So far in this course, we've focused on relationships between elements in a single compound. We've seen that the essential conversion factor between substances within a compound is a mole-to-mole ratio that you get from the compound's formula. For example, suppose I have 3.0 moles of H2O, and I want to figure out how many moles of H there are in there. Well, I can do this in my head. There's 2 moles of H for every 1 mole of H2O, so it should be 6 moles. But I can look at it this way too. The formula tells me that for every 1 mole of H2O, I have 2 moles of H. And I had to put the 1 mole of H2O on the bottom so that the units would cancel out there. So I can get this mole-to-mole ratio from the formula. The subscripts give me those mole-to-mole ratios. Now in this video, we're going to use that same technique to relate moles of reactants and products in a balanced equation. Let's look at combustion of octane. This is octane, which is a big component in gasoline. Okay, in worksheet 6.1, we learned how to balance this equation, and balancing that is going to give us the mole-to-mole ratios that we need to solve problems with this equation. So let's balance it like we did in 6.1. I start balancing an equation by putting a 1 in front of the biggest, most complicated looking thing in the equation and see where that takes me. When I put a 1 in front of this, I've got 8 carbons on this side, so I must have to put an 8 here. And when I put a 1 in front of this, I have 18 hydrogens on the left-hand side, so I must have 18 here. So what do I put there? A 9, right? If I put a 9 there, 9 times 2 is 18. And that'll work. Now I've got this whole side nailed down so I can figure out how many oxygens I need. 8 times 2 is 16 oxygens here. 16 plus 9 is 25 oxygens. So I need to have 25 oxygens on this side. Now I cannot just put 25 in front of that because that would be 50 oxygens. What I'll do, and what we did in 6.1, is know that if I take 25 divided by 2, 25 halves, that will give me 25 oxygens here. Because 25 halves times 2 is going to be 25. So I've got this equation balanced and I can use it just this way. Some people don't like to see fractions for the coefficients in a balanced equation. If I wanted all integers here, and sometimes the homework will ask you to do this, I will multiply all the coefficients through to remove any fractions. Since there's a divided by 2 here, I can multiply the entire equation through by 2 to get rid of it. So this also is the balanced equation. Now I can read this equation off in English. Here's what it means. It's a recipe for burning octane. It says take 2 moles of octane plus 25 moles of O2, and you're going to get 16 moles of CO2 and 18 moles of H2O. And you can take any pair of these things and relate them with a mole-to-mole conversion factor. You can say, suppose I wanted to figure out how much CO2 am I going to get when I burn some octane. This equation, this recipe, tells you that. So that's the mole-to-mole conversion factor that you would need to relate octane to CO2. So suppose I have a problem that says I have 7.5 moles of octane. how many moles of CO2 am I going to get from that? Now I can use this as a conversion factor. I need a balanced chemical equation to convert these things. Now, there's an important principle here that we're going to use throughout the rest of the chapter. And it is that in this problem, I am converting one substance into another substance. Now, you know how I put boxes around things that are important that'll show up on tests? I would put 2 boxes around this if I could, because it is the operating principle for the rest of the chapter. All right, that's very important. Where do you get this mole-to-mole conversion? You either get it if you're doing elements in a compound. You get it from the formula of the compound. Formula. What am I talking about there? It's exactly what I did up here. I got this mole-to-mole ratio from the formula of the compound. For reactants and products, get it from a balanced equation. That's where you get it. So this is the key to understanding all the problems for the rest of the chapter. And it's something that you should say to yourself immediately when you see a roadmap. Ask yourself, am I turning one substance into a different substance? If so, I need a mole-to-mole ratio. Where do I get it? From one of these 2 sources here. All right, let's finish this problem that I started here. If I have 7.5 moles of C8H18 and I want to figure out how many moles of CO2 I'm going to get, I'm going to use this conversion factor that I got from the balanced equation, and I have to put moles of octane C8H18 on the bottom. And this conversion factor tells me there's 2 moles of that for every 16 moles of CO2. So that's my setup. It's going to be 7.5 times 16 divided by 2. So it'll be 7.5 times 8, so a little less than 64, 63, 62, something like that. That'll give you how many moles of CO2 you've got. All right, we can do another one from this same equation. Suppose I want to figure out how much O2 do I need to burn (20 moles of octane. All right, let's figure out how many moles of O2 that I need. All right, if I have 20 moles of C8H18 and I want to get moles of O2, I say to myself, okay, I'm converting one substance into another. So what I really need is a balanced chemical equation that involves both of these substances. Here it is. Here, this equation tells me 2 moles of C8H18 is equivalent to 25 moles of O2. That's the link. So 20 moles I'm going to have to put the moles of C8H18 on the bottom so they'll cancel out. There's a 2 sitting in front of it, and on the other side there's 25 moles of O2. So it'll be 20 times 25 divided by 2, so that one I can do in my head. It's, what, 250, right? Now, if you're worrying about significant figures, I don't know how many significant figures I got here. At least one by the rules of significant figures. So I'd have to have at least one here in this. Suppose I knew this to the nearest mole, then I'd have 2 significant figures. So I would only know this one to 2 in that case. So whatever I'm starting out with here is what I'm going to end up with. How can I say that? Because this is exact. When you get these mole-to-mole ratios from the balanced chemical equation, those are exact. So whatever significant figures you've got here is how many significant figures you're going to have over here.